Hey guys, what's going on? So today we're going to be going over more of a deep dive into the covariant derivative. In the last video we talked about it, in this video we're going to talk about it, and in other videos after this one we're going to be talking quite a bit about the covariant derivative. So with that being said, make sure to hit that like and subscribe button. If you like this kind of content, also make sure to check out my Patreon page. Now let's get straight into the content. So today we're going over the covariant derivative again. We want to, I'm sort of structuring this so that we go over this covariant derivative a lot because it's really, really important in what we're going to be studying later. But anyways, so let's do a little bit of a review. So this was the picture we had developed before, where we have an extrinsic, we can develop an extrinsic definition for our connection. We also can develop an intrinsic definition for our connection. The extrinsic definition, again recall, was a definition that related our connection to acceleration vectors on our manifold. The intrinsic definition, recall, we used the metric, which is intrinsic to the manifold itself, and that's all we use to define this covariant or this affine connection. Okay, so we can define it intrinsically in terms of the metric, or we can define it extrinsically in terms of acceleration vectors. So recall also that the covariant derivative is a derivative that takes into account the deviation away from parallelism. So the covariant derivative, what it really tells us is it tells us the derivative, how something changes as it traverses some manifold. So that change is a change from parallelism. And this is what we came up with last time. Okay, so this was our covariant derivative. This is what that looked like. I also said that we were, this thing has a basis, right? This object has a basis, and this basis is through this realization that we made a while back, where this partial derivative was a basis vector. Here's that partial derivative as a basis vector. To make this even more general, this entire object is something that depends on spacetime itself. So everything in here has a spacetime argument. Okay, and so this is actually four entries, right? Because this is going to be x0, x1, x2, and x3. So this is like an x mu, if you will, right? So I want to distinguish it from this mu, however. So I just made it x, implying that this is a function of four variables. Same thing here. Then we have the basis vectors as well. So here's our basis. So this is all review. Now let's talk about what we want to do for a good chunk of this video. What I want to do is I want to prove that the covariant derivative, I want to prove to you that the covariant derivative transforms as a tensor. Now let's do this. This is our transformed covariant derivative. So here's our object, here's our covariant derivative, and what we want to do so here's our covariant derivative. The components, we defined this before also, the components are the components of the vector in which we're going, in the direction that we're going. So that's going to be these guys right here. And then this is our, this is going to be our basis. Okay. Okay. So now so this is going to be a little bit of a nasty calculation, but I really want to do this for really my edification, just to show you guys that these things really do transform as tensors, because I don't really want to take the things that I want to take for granted. I want to minimize. I don't want to just say this can be proven or this can be shown and then just not show it to you. Although I have done that in the past, I want to try to minimize that as much as I can. But anyways, I keep on diverting here, but okay, so let's go about doing this. So the way we're going to do this is through a bunch of chain rules. Right, so, okay, so this is pretty long. That's a pretty long and nasty, looking equation. But really, what we're doing is we're taking the derivative here. This is a chain rule, right? So this dyi by some dummy variable, okay? This is a derivative of some dummy variable. And then we have this guy here. And then what we have going on is a derivative of this guy, right? So the derivative of this guy is going to be, well, if I color code a few things here, here is the W. Here is, I'll do this x beta. Here's x beta. All right. And then here is yj. And here is yi. And then we have, let's see, let's do this in light green. Here's x alpha, and here's x alpha, and then we do yi, and then we have x alpha again, that's going to be in this color, and then we have x beta, let's see, that was in dark green, like that. So by color coding these, hopefully what I'm doing here is showing you how this is working. Right, so this is really just the chain rule, and then we have so we're taking the derivative of this guy with respect to this x. Okay, and when we do that, here's our x. We need to take the product rule, essentially. Right, so we have numerator here, denominator, and so we get this here, and then we get this part here by differentiating the we want the yi here. Here's our yi, so our purple, and then here's our x. All right, so we can see again by color coding this x, y, beta, and then we have our omega here, and this should, yes, okay. So once you stare at this for long enough, then you can see how this is a chain rule, and then you kind of do the same. You do the same thing, but for this term, okay. And keep in mind it's all being multiplied by this as well. Right, so I am not going to go through the color coding. You can stare at this for as long as you want, but I made sure to go through this as well. A lot of this is also coming from, if you also want an alternative explanation, you can go onto Andrew Dotson's page as well, and he goes over this derivation also. But you can, if you stare at this long enough, then you could see that this is the product rule. Okay, this is all product rule where of this right here. Okay, and then we group terms together, right? So I will go through color coding again just for your edification. So there's purple. And then here's our purple. I'll mark the Y's in purple. And then I will mark, oh, there's another Y. And then the X's were in light green. Right, so x is in light green. Okay, so this, all this together is along with this guy, right? So that guy is going to be out here. So when we multiply all this out together, we get this right here, right? So here's our omega. Here is our x beta. And then another x epsilon, right? So x epsilon is right here. All right. I said I wasn't going to color code, but I did just for my own sake of sanity, and also hopefully to help you guys as well. And so we do the same thing, multiplying everything out here as well. Okay. Multiplying everything out again, and this is that third term. Multiplying everything out again, this is that fourth term. So we have a lot of ugliness going on here, right? So we have this guy, and this guy. But not to fear, a lot of this is going to go away pretty quick. So let's take a look now. So collecting everything, beta, phi, epsilon, alpha. We're just looking at these guys here, beta, phi, epsilon, alpha, and we're summing over the purple terms. Okay. And then we have this term here, this term here, and this term here. Right, so I'm not going to go, again, you could pause the video for your own edification if you want to do that. Again, I've pre-written it out already. This should be pretty self-explanatory, I think. It's just a lot of calculations. And then we have this guy. So to get from here to here, right, we have, so these guys are going to drive their indices to be the same. So when we do that, we get this. All right. And then same thing here, right? So alpha is going to be driven, or phi is going to be driven to alpha, right? So phi driven to alpha, and all that happens here as well. Same thing here. A lot of indices are going to be driven to each other. That's this term that we see right here. And then this term right here is sort of the same deal, right? So epsilon going to be driven to gammas, or vice versa, right? These Kronecker deltas, again, they are just driving indices into each other, which makes things a lot more compact and easier to deal with eventually. Okay, so we have U beta. So this looks like we can actually recover this, right? Because we have this guy and this guy here. So this term here and this term here, they get all packed into this. Then the rest gets packed into the second term here. All right, so remember that this is the derivative. This is the derivative, we said, of omega in the direction of u, right? So of omega in the direction of u transformed into some different coordinate basis. And so what that is right here. So it looks like we have a covariant derivative regained, but then we have all this right here. So this part right here, this is in red. It's going to be this guy. So now we are left with this right here. Okay. this term right here we're going to find is actually equal to this term. So let's do that. So this term is right here. We're going to split up the, let's see here. What are we doing? This is the double, so we're splitting up the double derivative, right? And so this should be x, let's see, x alpha, x beta, x dx gamma. These are dummy indices, which is why we're able to swap, okay? And then we keep this delta up here. So this is literally just this with the dummy indices swapped, right? And so this should actually be, let's see here. We have, okay, so to get from here to here, we have, okay, well, this term right here is right here. And then x or y gamma, that's what's spinning me off here, y gamma, right? So y gamma, so what we're left with, and here's that y gamma. That's why I was getting a little bit off. But these guys right here, right, so these guys are essentially going to cancel. You can think of those guys as canceling. And then we have this guy right here, and then this is equal to this guy, right? Because if we say that this is equal to the Kronecker delta, right, xi, xj, yk, well, this is a sum over k, so this is going to be the Kronecker delta if I is equal to j. Because you can think of these as like getting crossed out, right? You can think of these guys as getting, oh wait, my face might be in the way. But these guys is getting crossed, these guys getting crossed out. And then, so we can expand this, right? So we can expand this, here's xl. So we're going to expand this, we're going to take the derivative of this. We're going to take the derivative of this, say, essentially taking the derivative of both sides of this. So our derivative of this is going to be 0. Derivative of this is going to be this, right? And when we do that, we get this guy right here and this guy right here, right? Because this is, again, this is a product rule, right? I always get the names mixed up, product rule, chain rule. But this is one of those rules where we get this, and then just because this is equal to 0, we can subtract this from both sides. We get a minus on this side and a positive on this side. And so just by looking at this and looking at this, we can see that, or actually we're actually looking at this and looking at this, right? So we're comparing indices, right? So in this case, delta and I are going to be these two are matched, epsilon and k, beta and j, L and K, and alpha and epsilon. All right, so just by looking at this and this, then we can infer this. And when we do that, we see it's equal to this. All right, so that was a lot. We're coming towards the end, though, because what that means is that all this is 0. So that means we just get this. Right, so if all this goes to 0, then we just get this. So the transformed covariant derivative is just the covariant derivative. It actually didn't change. Okay? Which means that the covariant derivative transforms as a tensor, right? Because again, the tensors are things that uniquely are invariant under, or not invariant, right? They have a unique transformation under a coordinate transformation. And so given that this thing is actually invariant under a coordinate transformation, we could say that this is a tensor, right? So this here is a rank 1, 0 tensor, okay? And that means that if we multiply this guy or if this guy's acting on a vector, a covector, it'll give us a number. All right, so this thing is a rank 1-0 tensor, so that means it's a map for a covector. We can also contract indices with a metric tensor. And so that means, well, if we have this we're going to say this is this here again we said was a tensor. We've now proven that it transforms as a tensor, so it's a tensor. And this thing here will be called a covector. So if we act on this, which we're going to say is this, but this is just shorthand notation for right now. And then we'll replace things later. But if we act on this with this, and we get this right here. Well, this here we said was alpha Kronecker delta, right? So if this is Kronecker delta, then we get this, and we get this. Okay. Well, this we said was this. So G alpha beta with covariant derivative. Covariant derivative has a basis. Well, that's going to look like this. So the metric tensor acting on this object here, acting on this vector, is going to give us a covector. So we can think of the metric tensor again as raising and lowering indices for an object like this. Okay, this is what I want to get to now. This is going to be the theme for a couple of videos going forward. I'm calling this the hierarchy of spacetime. What we've managed to do is I want to go back to this picture really quick actually. So I'm summarizing this picture, extrinsic and intrinsic definition. The extrinsic is the green path, intrinsic is the brown path. Brown path, green path, okay? At every point in space, we can erect a vector. That vector can describe the velocity of an object, it can describe the form momentum of an object, it can describe anything you want it to describe. As long as it's a 4-vector, it obeys Lorentzian transformation properties and all that sort of stuff. We can erect a vector at every point in spacetime. We also have now the ability to say that if these things live in vector spaces, they can also live in metric spaces, and if they live in metric spaces, then we found out that there's a rank 2-0 or a rank 0-2 tensor that mimics those metric spaces. Okay, and those are these guys. These guys were then used. We can use them to intrinsically define coefficients on the acceleration vector. And this also accounts for parallelism. We also use these guys, right? So these guys are these things again. They're the coefficients on an acceleration vector, the acceleration of these a mu's, right? So a mu and a mu, and yeah. So we have these things help us define this object extrinsically. Our metric tensors help us define this thing intrinsically. And then, ultimately, these guys are used in the covariant derivative. So, I like to call this a hierarchy of spacetime because this looks like a pyramid. And pyramid has a top to it. So, somewhat like a hierarchy, like a food chain or something like that. Here's our manifold down here. So we're erecting pyramids. We're erecting pyramids at every point in space-time. They're sort of abstract pyramids, though. This is the abstract pyramid of space-time. And so this picture, I really like. It really, I think, succinctly helps us understand where things are coming from. The color coding, I think, helps as well. And yeah, so all four of these guys are essential in the construction of this hierarchy of spacetime, or the architecture of this spacetime, if you want to say it that way. But anyways, with that being said, I hope you guys like this kind of content. Make sure to hit that like and subscribe button, and go to my Patreon page if this is the kind of content you're interested in. I'll see you guys in the next video.